All right, I think we can get started for the last topic today. It's our pleasure to have Margaret Thomas from here and Purdue, who will be speaking of O-minimality and definable topologies.
Thank you very much, Ben, and thank you to the organisers both of this workshop this week for the opportunity to speak, and the powers that be behind, which I think is principally Jacob, behind this year. This very nice special year, already very nice, a month old, and the opportunity to be here, which is marvelous. So I am very interested in lots of the topics of this special year, and have in fact been involved in my time with various aspects of them, especially things like effectivity questions. That's the latest thing. Things like effective capability applications and so on. But none of the things that I've been working on to that effect are really, at the moment, I feel sort of in any way ready for public consumption. And that's why this year is a great thing, because I hope that will change in due course. But what that means is that what I've chosen to talk about today is something that I have been working on for a very long time as well. Maybe this is a program that's been going on maybe the last 10 years. And so there are lots of things that I could say about this, but I do sort of feel as though this is the moment where John Cleese should appear on his desk in the sand with the waves washing around and saying, okay, and now for something completely different, because this isn't going to be very like any of the other talks in this conference, I think. So what I'm hoping is that this, for your benefit, this will be, what you'll get from this is some light relief before the dinner tonight. You can sort of completely just sit back, relax. If you get something out of the next hour, that will be fantastic. And as discussed, I will be here all year if people want to talk about things more. Maybe I should say up front what I'm perhaps this is the principal aim. I'm going to talk about a lot of things in a program in O-minimality. It would be wonderful if people could see ways in which this could be applied and used, and maybe even motivate the next directions that this will go in, which I'll say some more about at the end. But for the rest, just sit back and there will be pictures as well. Okay, so without further ado, I sort of felt as though maybe I have to start from the beginning. So what is our context? It is an O-minimal structure. We'll get to that in a minute, but just structures, right? I know Gal gave some introduction last week, but I'll go through this quickly anyway. Think first order structure, fixed ambient background domain R, and some fixed first order language L. Though definable for me means definable by an L formula with parameters from R. If that's completely meaningless, you can think of it as a set system, where you think of L as actually a collection of sets in some R's to the N's. And we're building these collection of sets generated by, so some Sn for every N, where Sn is a collection of subsets of R to the N, generated from the sets in L by closing under finite Boolean operations, which correspond to and or not, Cartesian products, which let us use dummy variables, coordinate projections, which corresponds to existential quantification, and by including taking fibers, which is where the parameters come in, and by including diagonals, which lets us talk about when things are equal to one another. So you have such a collection of sets. So this is really our focus. When we talk about structures, we sort of really have in mind the accompanying collection of definable sets. None of that is specific to O-minimality, right? So for a model theorist to talk about definable, it really, you have to say what structure you're working with. But for us, we're working with O-minimal structures, and we have the O-minimality axiom here. So if you have an ordered set, so a set with an ordering, and your ordering is in the language, and if you prefer, that means the set of pairs, x, y, where x is less than y is in your language, then your structure is O-minimal if every definable subset of the line is a finite union of points and intervals. So you can only talk about intervals if you have the ordering, so I mean with respect to that ordering, where the endpoints can be infinite. Fantastic. So in other words, the definable subsets you get in the line are no more than those that have to be definable because you have the ordering. Okay, but it turns out there are lots of examples, and so one of the things that I want to do in the course of the talk today is to maybe give you a hint about some of the proofs or some of the results to the point where you see why I'm working in this general framework. Although any of the statements that I actually make, you can just think of your favorite O-minimal structure if you have one. Okay, but for those who maybe want to expand their horizons a little bit, here are things that are O-minimal. All right, any ordered set, any linearly ordered set. So particular interest dense linear orders without endpoints. Any ordered vector space over a field. It's a fact that if you have an ordered group that is O-minimal, it's an O-minimal if and only if it's divisible ordered abelian. And if you have an ordered field, it's O-minimal if and only if it's a real closed field. So this is supposed to give you some sense of what kinds of things might show up in the background, the things that I'm talking about. Although, of course, lots of people have their favorite examples. And here's a slide which lists examples where your favorite example probably will appear. The semi-algebraic sets, which of course is the real field as a structure. Globally sub-analytic sets, which is the structure Rn. So the expansion of figures by real analytic functions on an open, the real analytic on an open neighborhood compact set. Rx, right, add the total exponential function. None of these is a trivial result. These are all big theorems, right? You can combine those two together. That is also not for free. Some of these, of course, Jacob mentioned in his colloquium talk a few weeks ago, but this is just to remind you. So Rnx, which is many people's favorite, I think, although maybe that's what we'll see by the end of this year, I don't know. Because here's a broad class of examples that I'll just throw into the end of the slide fit, which is the real field expanded by some so-called quasi-analytic class of restricted functions. So what I mean by that is, I'm not going to define properly here, but a class of functions that's broader than restricted analytic. So the idea being that you have functions somehow given by power series, which might not converge, but they're uniquely defined by those power series. So the Taylor map is injective. And an example of that would be Algebraic functions, which maybe some people have heard of. And I'm saying very little on this point because I'm going to leave Patrick to say more about that in his talk, because I think he's going to do that in his talk tomorrow. But there are various examples of this flavor, and there are some references there for those who are interested. Okay, so again, and all the statements I'm going to make today, you could just think of as holding in your favorite example. But I'll try to give you some idea of why we're working more generally. So what are we doing? Very good question, right? So a little history lesson here, not really, but a little background maybe. So again, take your own favorite O-minimal structure. If you've ever worked with these things, you know that there is a natural topology on these things, right? We're going to call that the Euclidean topologies, the topology induced by the ordering on the line and then the product topology on R to the n. And classically, if I can use that word, this goes back to the 80s, right? But classically, O-minimal structures viewed through the lens of this topology generally regarded as fulfilling Grothendieck's vision of a topology of multi. Okay, and the key thing is the strong finiteness properties that it says. So things like, these are key features, right? Definable functions in one variable are finitely piecewise monotonic or constant. So the monotonicity theorem. Okay, so piecewise, you're either constant or you're monotonic, and there are only finitely many pieces. It's true for any definable function. More generally, you can decompose definable sets. So we had in the line, of course, by axiom that all definable sets in the line are a finite union of points and intervals, so finitely many connected components. Same is true with respect to definability for all definable sets in all dimensions. And you can, in fact, decompose them very nicely into these so-called cells given by continuous definable functions. And if you assume a little bit about your structure, which, again, I'm guessing is true for the favorite structure of anybody in this room, you will also be able to make those functions CK or find CK functions that do the job. Okay. So what does this mean? These are the big take. Yes, go.
Just to be sure, are you taking a structure over a field, or it's even a general structure?
It can be anything.
But
it can be
CK
anything.
you can get with.
Oh, but the CK bit, you need a field. You need to be able to talk about differentiation. Sorry, to be able to talk about differentiation. So you need to be able to. I mean, so I'm being very specific there. Whatever you need to be able to do that. But typically, you just say over a field. Exactly. But everything else holds in general. So these are the kinds of things that are consequences of that. There's no infinite discrete sets, no oscillation, no pathological geometric behavior, no space filling curves, counter sets, and so on. So all these pathological geometric problems go away, and you have example, I already mentioned this, that definable sets have only many definable components, but also from that, or sort of you can see is closely related to that, the idea that finiteness bounds are uniform families, so-called uniform finiteness. Right? So if you have a set, then its finite fibers are uniformly bounded in size, defined by a definable set. And this also gives rise to a good notion of dimension. So without saying more about exactly what that is, you can derive it from the solid decomposition. You have something like this so-called frontier dimension inequality, where the dimension of the frontier of a definable set is strictly smaller than the dimension of the set. So I mean by this thing frontier, just because it's been used by other people in other talks in other ways. Okay, so these are all classical properties, right? But O-minimality and its underlying topology are inextricably linked and extremely important for all sorts of applications. Yes? Please.
If I have a map, will it be true that removing something on the basis, the cohomology of the fiber is locally constant?
Good question. I should know the answer to that question. I don't. Is everybody?
It's delicate because one has mapped where the type of the fiber vary continuously. But in algebraic geometry, it remains true that the cohomology does not change.
I think there is a kind of definable Ehresmann theorem. There's definable triangulation and
Definitely look, see you guys, but I'm not sure. There's a general consensus that we think it's true, but I'd have to go. Yes, it's a good question. Okay. So this is one part of the history lesson. Here's another. There's a long-running theme in O-minimality to characterize, especially from a topological viewpoint, characterize the objects that are actually definable in your structure, your O-minimal structure. So I'll give you an example of that in a minute, but as I've said there, in particular in terms of topological properties. So for example, here's some examples. So again, we're going right back to almost the beginning. Pillay characterized definable groups. So a group G is definable in an O-minimal structure, that is definable in an O-minimal structure R is a topological group with a natural definable manifold topology. And if you're actually working over the reals, this is a Lie group. So when I mean say definable group, I mean the set G is definable and then the group operation you can write down with a formula, or you can think of the set that defines it as being defined. So, just to push that a bit further, Van den Dries characterized these definable manifold spaces, and I'll say what that characterization is in a little bit. So I call them definable manifold spaces. Van den Dries called them just definable spaces. There are going to be lots of spaces in this talk, so I have to just be able to distinguish this kind of space from other spaces. So I call them definable manifold spaces. Johnson looked at interpretable sets in O-minimal structures, so sets that are quotients of definable sets by definable equivalence relations, and also showed that they have some kind of piecewise Euclidean, should be looking at that, right? Topological structure similar to these spaces, these definable manifold spaces, and again, they were used by Bakker Brunebarbe Tsimerman.
Sorry,
Yes.
what's the difference between interpretable and definable? Because I thought you could take quotients definably and it was fine.
Only if you have enough underlying assumptions on your O-minimal structure. And I am not putting those in there. So yes, in general, that's fine. But just to be more literal, then I should be careful.
Sorry, I'm just a little confused. What part of this is Pillay's result? What did he prove?
Well, I haven't really stated it, precisely, but that's the first bullet point.
Oh, okay.
Is that?
Sorry, so you're assuming that it's a manifold, but that the group operation is not smooth, or why is it not a Lie group by definition? I'm just confused.
You don't necessarily, the language you're working isn't necessarily a field.
Oh.
Again, probably this is a little bit unsettling because if your favorite structure is a field, I should say that our result, I should emphasize this, our results will work on your favorite O-minimal structure, but in general, these are more, there's something to say if it's not necessarily a field or a group.
Oh, I see. Never mind. I understand.
Yeah, thank you.
In some standard structure, does it make sense to speak of a definable Riemannian manifold?
That's a very good question as well, and that's not clear exactly what the answer to that is, I think. Yeah, yes, it makes sense, but what exactly you get, it's not, yeah, these are good questions. Okay. So enough about manifold spaces. Another flavor of this kind of question is to look at another very simple example, that of a linear order, right? A set together with an ordering, which is a definable relation. Well, these were looked at by Andújar Guerrero and Ramakrishnan in various combinations about 15 years ago, who proved various embedding theorems for this. I'll say some more about this later. And I don't know if this was their motivation, but they achieved various applications to economic preference theory, which maybe is not what you were expecting. Again, I'll say something about that later on. Okay, and then from there, other things that perhaps should be mentioned in this context. One of them is a very small study of definable function spaces in this general setting, which I did about 20 years ago. The data is somewhat misleading there. But really that idea was taken up and run with by Walsberg, who considered definable metric spaces and looking at properties of these, characterizations of these. That, just to say for now, is the definition is what you think it is, except maybe I shouldn't say that, but I think it's probably what, if you had to write down the definition, you would write down the correct definition, but I'll give you the proper definition of it. Okay, so it's a natural extension, especially the last part of this list, to say, okay, well, what about in general topological spaces that are definable in your general and O-minimal structures? What exactly does that mean? So I need to make this precise. And again, this is a very general definition that has nothing to do with O-minimality. But again, I hope it's what you'd write down if you just naively tried to write down a definition of what it should mean for a topological space to be definable. It's a definable set together with a definable family whose fibers give you a basis for topology on that set. Okay, so the simplest definition you could come up with, this definition really goes back to the 70s. But in the context, so we're going to consider this in the context of O-minimal structures. But it's definition that has nothing to do with O-minimality. So. Okay, so what are we interested in? What kinds of theorems might we be interested in trying to prove? Right? So classification of definable topology, what does that mean? Right? So a couple of different directions you could go in. One is decomposition theorems. So think cell decomposition, right? You can partition your definable set into nice pieces given by definable functions, something in that spirit that says you can decompose your topological space into nice subspaces, whatever nice means. Okay. Or maybe you're interested in something a little different, like an embedding theorem where, well, I've even given two different examples of what that could mean here. One is maybe there are some universal or almost universal spaces that are definable into which you can always embed your space. Or maybe, and this is a long-running question, I'll say something more about in a moment, when is your definable topological space affine? So for us, affine means definably homeomorphic to Euclidean space, to some set, definable set in R to the n on which you have the underlying Euclidean order topology. Okay, so that's what we mean by affine.
Just to make sure I understand, on the previous slide, if I took the Zariski topology, that would not be definable, right? Because there would be too many open sets.
Okay, so I said this question here about affineness was actually a running theme. So this is the characterization that Van den Dries gives of these so-called definable manifold spaces, that they are affine if and only if they're regular. That's the result that I was alluding to earlier. And Walsberg, who looked at these definable metric spaces, showed something useful, which is that they're affine if and only if they're, quote, definably separable. Whatever that means. Now, the reason I mention this here is to hint at something that you have to care about if you want to get into this, which is that in the general O-minimal context, so in particular outside of the reals, you cannot rely on sort of countable indexing of things. You have to have a perspective where your definitions have to make sense, but you don't have access to this perspective of the reals. And so what I'm trying to say is that you have to think about continuous analogues to all of these classical topological notions that are defined somehow using the natural numbers. So things like separability, first countability, second countability, just don't translate over into a general setting. They're not definable. So you have to think about what these notions should mean for a general O-minimal structure. But at the same time, you don't want to stray too far from your roots, right? And so on the one hand, part of the job here is to figure out what the right definitions are in the general O-minimal context, if they don't already exist. And on the other hand, it's to make sure that over the reals, your definitions still agree with the classical definitions. Okay, so again, I'm just mentioning this to give you a flavor of what kind of things go into this research program. But if you've got your favorite O-minimal structure and it's over the reals, every time I stick the word definably in front of a classical topological property, you can just pretend you're working with the classical topological property if we've done our job correctly. Okay, so that's probably what I was just putting at the bottom of the slide there.
Sorry, can I ask, by apple, do you mean definably homeomorphic to like a sub of Euclidean space, or?
I think I said that, yes, so some subset of some R to the n, looking at the subspace topology induced by just the Euclidean topology. Exactly right.
This can be done for C infinity as well. So C infinity embedding for a C infinity definable.
That's a good question, but again, not something you can say in general, I would guess, but certainly an interesting thing to ask. Yeah. So in general, these things, you're just looking for some definable function, which is then is going to be well, it depends what you're assuming about your structure, if it's going to be continuous or CK up to whatever K you want, but in general. Sorry?
Separable means what in this?
Separable in the classical sense. So containing a countable then subset. Definably separable, I haven't defined yet. I will later on. Maybe very quickly, depending on how much time I have.
And it cannot be any quicker than what you do right now. Yeah. Yeah. So separable meant what? Can you repeat that?
So classically, separable is the same definition that one learns in real analysis, so countable dense subset.
Countable?
Dense subset.
Countable dense subset.
Is that okay? So again, if you see, so my hope is that if you see a word like that, you think it's what you think it is in the context that you're thinking about. That's the goal. Again, I don't want to dwell too much on that aspect of things for this talk today, but it's in the background. That's all I'm really trying to get at. Okay, so what are we up to now? Right, so what are we going to say in this section? I want to present to you some results of this flavor. That's the general idea. Maybe give some hint about the kinds of things that go into the proof, but again, not expecting follow all the details or anything like that. Just help you read the papers if you're interested. So I promised pictures. Okay, so examples. I think we could use some examples and so let's start with some very simple examples of things you can define. But with the goal of also pointing out that even simple examples are very different topological properties. Okay, obviously when you think about it, the Euclidean topology, the underlying order topology, is in fact itself definable, right? So if I draw a picture and I just draw it in the line for the sake of simplicity, and I have a point, basis of open neighborhoods, open intervals, definitely definable. Clearly extend this to higher dimensions. Let me call that tau E for Euclidean topology, okay? Separable, metrizable over the reals. You can also define upper and lower limit topologies, left and right half open interval topologies. Right half, this is the classical solid by line. So we have I do this. Left half open interval topology. Right half open interval topology. Definitely definable. Nice and simple, right? But classically, over the reals, not metrizable, totally disconnected, not second count. Okay? Okay, let's complete the picture with a list of silly examples. Discrete topology also defined, right? Because of metrics hanging around, we've ended up calling this tau S. So I apologize, it's not necessarily intuitive, but that's tau S. And of course, that's also just totally disconnected, but this one isn't separable. So even in just the most ridiculously simple examples, we have various topological properties showing up. Okay, what else? Let's look at something slightly less simple. Okay, classical examples of topological spaces designed to exhibit counterexamples, pathological type properties, right? Things like the split interval, or the definable the double arrow space. I stick the word definable on the front because clearly this is also definable in any O-minimal structure, just with the ordering. It's the two lines 0, 1 on the unit interval 0, 1 classically with the lexicographic order. I'll draw a picture in a minute, but there are some properties if you're interested. We can of course generalize this, and we do. So that's the thing I'm going to draw the picture of. So we call this the definable n-split interval. It's an n-line version of the classical double arrow space. So you've got n lines numbered 0 through n minus 1. And this is so I'm just going to draw pictures, so you don't try and read the slides too hard. What this is saying is that the points on the top line have basis of open neighborhoods. I've done this the wrong way around. It's fine. I'm going to confuse myself, but you don't need to worry about that. So basis of open neighborhoods for the things on the top line. Look, this is where I'm confusing myself, right? Yeah. Yes. I should have started at the bottom, which is what I intended to do. The basic open neighborhood of a guy on the bottom looks like this. Right? Sorry. Apologies. The basic open neighborhood of a guy on the top looks like this. Okay, and all the points in between are isolated. So, okay, so that's what that says. That's the picture that corresponds to that. So, lexicographic order on n lines. Okay, it's definable. It's an example. Just pictures for now. Put some properties there where it's over the reals, again, separable, not compact, second countable, or traceable. Don't worry too much about that. Here's another classical counterexample in topology, the Alexandrov double circle. Maybe I can put this one over here, if that's all right. So it's again hard to pass if you don't know what it says already. So just look at the picture. You've got two circles, C1 and C2. Take a point on the inner circle. What is a basic open neighborhood of this guy? It's a sort of arc around X, and then imagine extending this out to the corresponding point on the outer circle, and take the arc missing the point corresponding to X. So this inner arc together with these two pieces on the outer circle are the basic open neighborhoods for this guy. And these guys are isolated on the outer circle. So this is a classical counterexample in topology because it's compact but not separable, not metrized. Okay. So again, that's definable if you can sort of talk about this map that takes points on the inner circle to the outer circle, and the way I've written it there, you need some field operations. We want things to be very general, so we're going to take this and turn it into something that you can define without such operations. And in fact, generalize it a little bit to something with n lines again. So it's the n-line analog of that example over there. And it's just, so the bottom line is then the inner circle. So you have its basic open neighborhoods look like this. The point down here has basic open neighborhoods that look like this. And all the points on the other lines are isolated. Okay. Again, examples, but this one is what we call the Alexandrov.
All right.
Yes, Gal, sorry.
When you say that this, I don't know, something that you define is compact, Do you
Yes.
mean it's compact for every R as we have set it up, or do you mean it's compact when I interpret in R, or do you mean for some correct definition of compactness?
Right, this is part of the question, part of the things we have to care about. So I've tried to be careful on these slides and only use the words for topological properties when I've said over the reals, and then you can make sense of it in the classical sense. Right, so this one I've just drawn up on the board, I've flipped the slide, but this is the setting. When R is really the reals, we can talk about compactness, separability, metrizability in the classical sense, and then it's what you think it is. If we weren't over the reals, we would have to make sense of those definitions. And I will try to say something about some of those as they come up later on. But for now, I'm just drawing pictures, partly just to show that if you just cared about the reals, you could already see there were different properties arising. And that's all to worry about right now. Just a brief remark before I go on. I'll do a couple more over there, but for now, just to make, I think it'll be relevant later. We'll see where we get to. The degenerate cases of both of these two, imagine it's not just the subspace at the bottom. It is, imagine this thing collapses down to one line. And so what you get is the Euclidean topology. If you just have n equals 1 in either of these two cases, get the line with Euclidean. That we may get to the point where that shows itself. All right. Okay, a couple more examples. This one I definitely need my notes for. So we don't need that anymore, so that. So the one that's here on the top is again something over 2 lines, but it's a bit different. So this is fun. Okay, for some definition of fun. The points down here, their open neighborhoods look like the point itself together with intervals upstairs to the right. That's your basic open neighborhood of a guy downstairs. Upstairs, your basic open neighborhoods look like half open intervals to the left. Okay, you can define this, right? And what happens if you do? Well, this is the first thing up here. It's Hausdorff, but it's not regular. So the bottom line is closed. And it doesn't satisfy something we would call the frontier dimension inequality. You take a definable subset in here, and you look at its sort of dimension with respect to this topology, tau, the dimension of the frontier should be less than the dimension of the set itself. But the frontier of the top line is the whole of the bottom. So if nothing else, you can sort of think about that for the rest of the talk. But I should give you one more example, because so far everything has been in one dimension. I'll at least give you one example that's in 5 dimensions. And so what we have here is topology on R squared. But again, I'm going to have to put something in there, field language, to be able to describe to define this thing. But it's really simple. It's just saying you've got, so this is R squared, and definable open neighborhoods of points look like balls with, if you will, the graph of y equals x squared removed. So maybe I should make all these lines dashed, actually. Okay, and you can define that, and you get a topology, which is strictly finer than the Euclidean topology, so it's Hausdorff, but it's also not regular. Can't separate the closure of an open neighborhood of x, one of these guys, from that ray, that x squared line. Again, just going to sort of put those there and let you think about them. So with some extra ammunition, we can define a variety of examples, various different classical topological properties if we're working up with the reals, or different properties in a more general sense if we allow ourselves to think more broadly. Okay. Is this visible? And maybe I should put this. Okay. All right. I promised you also a definition of definable metric space. It's what you think it is, I said, but let me put it down anyway, because it gives you, of course, a whole class of examples.
Just quickly,
yes, please.
Can you tell us yet the definition of the dimension in general?
Of?
For a general definable topic. Is that, sorry, on the last slide, it's.
I guess I didn't write it down though.
Oh, okay.
So. Yeah,
No, that's okay. I was just wondering.
no, you didn't miss anything. I was just sweeping that under the rug. Dimension of, based on the dimension of the neighborhoods. Anyway,
What is some sort of how
I mean,
nested in
so
sets?
everything is definable set, so you also have you have a notion of dimension of definable set.
Okay.
If I want to talk about local dimension with respect to topology, I would have to be a bit more careful, but I haven't got to that point yet. Okay. Yes, you can define metrics or pseudometrics if you have the right language in which to do so. And you would, well, the only thing actually when you start writing it down is you realize, of course, you're not mapping into the reals, you're mapping into whatever R is. And then you see where that takes you, is the point. So if you have a map D, which is on some definable set X, where D satisfies all the correct axioms, you would call it, and it's definable, you would call it a definable metric or pseudometric. There's nothing particularly deep here, is what I'm trying to say. And in this particular setting, which is the one Jacob was asking about earlier, you do in fact have the so-called elimination of imaginary. So you have that you can refer to equivalence relations definably. And so you can take any pseudometric that's definable and turn it into take the appropriate equivalence relation and get a definable metric space from that. Again, I'm not going to use any of this, so I'm just putting it there for interest's sake, if that be of interest. And there are genuinely examples that you can write down that have some content. Okay. Right. So I should actually get to some statements. How am I doing? The time. Okay. All right. So what I would like to do is just more or less see how far I get and present to you some attempt to answer some of those questions that I raised earlier about how to classify these spaces. Okay. But rather than just write down, here's a theorem, here's another theorem, and so on, let me start by trying to give you some sort of left field, I don't know if I want to say motivation, but certainly inspiration for what such a theorem could look like. And the left field in question is set-theoretic topology. So this isn't really particularly relevant actually for the content of what I'm talking about, but it somehow inspires the type of statement you might try to prove. So going back to open problems in topology, 1990, Grunebarbe has a paper on something which I'll get to later in the talk about perfectly normal compact spaces, which contains this, really it's a question. I framed it as a conjecture because it's clear that he's leaning in the direction of this being the true correct statement. All of these statements have the form, which theoretic axioms are they consistent with? We're not interested in that for our purposes at all today. So you can ignore those kinds of statements. So if I ignore those, I would get a statement that says the class of uncountable, first-countable, regular Hausdorff topological spaces has what he calls a three-element basis. And when you unpack this, what it means is that each such space contains a homeomorphic copy of at least one of some subset of R with Euclidean topology, a subset of the organflow line, or an uncountable discrete space. So it contains a homeomorphic copy of one of those guys on the top of the board over there. Every such space contains a homeomorphic copy of one of those guys at the top of the board.
Can you repeat what is a Sorgenfrei line?
It is the right half open interval topology. It's that one. That's so. Maybe I should have just said that. I will say that for the rest of the talk. It's much easier, yes, to remember. So then there's some history to this. It's not true if you don't assume first-countability, which is a big result of Moore, but otherwise not very much is known about this particular conjecture. Okay, maybe that's a fun fact, don't know, but maybe if you're a set-theoretic topologist, what you really care about are the exciting, complicated spaces anyway. But you could say, well, if you're working with O-minimal structures where things are supposed to be nice, this really should hold. And the good news is it does. So this is joint work with my former student, Pablo Andújar Guerrero, as is everything in this talk. For the purposes of the statement, I've put everything in the line. So I've just taken R, I've taken X, a subset of R, and it's infinite T1, which I hope is an uncontroversial requirement, definable topological space. Then there is an interval whose subspace topology is one of the four guys at the top. So if you take a definable topological space of any dimension, if it's infinite and T1, it's going to have to contain a one-dimensional subspace, which is homeomorphic to some interval, which then contains an interval which has one of those topologies on it. So if you want to get into the nitty-gritty, which I have done, and I will spare you, what exactly this means for the formulation of this conjecture, here is an example of what it means. It means that if you're working over R without any extra structure, you can take your basis to be the whole real line with the three meaningfully different topologies out there. In each case, discrete, right half open interval. If you want this to be all definable, then you have to assume some extra things in the language. But again, if you're assuming all of those anyway, then. So the conjecture holds for O-minimal definable topological space.
So for R,
Yes.
this is sort of, unless I'm confused, this is like from definition of O-minimality, right? Like if you have something in R, or I'm missing something. Can you explain why? Because I thought if you're inside R, the definable sets with intervals, right? So what am I missing?
The subspace topology is not necessarily the Euclidean topology.
I see.
But it gets better, because if you assume Hausdorffness as well, you can decompose your space into finitely many points and intervals, on each of which the subspace topology is one of those guys at the top. So it turns out that actually what you expect, this is the point, it's what you expect to hold. But it turns out it does actually take something to prove it, which we did. Okay, so that's what that statement says. So again, if you assume that it's Hausdorff, there's a finite partition into subspaces of these kinds. Again, using cell decomposition, you can generalize that to one-dimensional definable topological spaces. Sort of imagine how that would decompose. Okay. Now, I was going to try to say something about the proofs of these two results, just to give you a flavor of what goes into proving this kind of thing, and why I do care about working in O-minimal structures in general. I'll see how this goes. All right. Again, I said it would be a little quick, so I'm not expecting this to be entirely tractable, but let me throw at you the names of things that come up in the process, and it gives you some idea, even if the details are a little hard. I hope that's all right, just in the interest of time. So again, this is theorem one. So the first result, we're just looking for a subinterval on which we have one of those four topologies. It's infinite T1. Fine. The key tool is this guy, the E accumulation set of a point X. So you've got little x in your space big X. What we're looking at is all the tau neighborhoods in your topology of that little x, right? And you're looking at all the points that are Euclidean accumulation points of all of those sets. Now that's a little difficult to parse at first reading, so let me give you some useful things to help you think about it. The first is that if you take some other point y is in the E accumulation set of X, if and only if y is in the Euclidean closure of all the tau neighborhoods of X. And moreover, if you're T1, you can show that this set is empty if and only if the point X is isolated with respect to your topology tau. Maybe that helps. Okay, there's something to do, but then, okay. Now, by a saturation argument, so model theory enters the story. We have to pass to some bigger O-minimal structure where we can realize some things. I'm not going to say what in the interest of time, but there's some kind of compactness, there's some argument going on here that requires going to some bigger O-minimal structure, some elementary extension, where you can identify, you can realize that some collection of sets has a point in their intersection, and then you can pull that back down again. It's hiding in the background. But the bottom line is that you can prove, this is finally I get to your definition, Chris, that the dimension of the Z accumulation set is smaller than the local dimension at x, at little x, which is this thing.
My question was stupid, right? You always have cell decomposition, so it's
So you
just
can,
like,
so in,
okay.
you're good, we're good. Okay. I'm just kidding. Okay. The point is that if you're working as I am at the moment in a one-dimensional space, if the dimension of the space is at most one, then the set EX has to be finite. So we've got finitely many points. What can we do with them? We can use them to build a basis of neighborhoods for this topology tau, which then lets us partition things in the way that we want to, or break them up in the way that we want to. So let me say this fairly quickly. But again, it's an O-minimality fact, because of the nature of sets in the line being finite unions of points and intervals, that you've got Y in this E accumulation set, so it's in all of these, it's an E accumulation point of all of the now neighborhoods of little x, the big A's, if and only if you can park an interval to the left or an interval to the right inside of every neighborhood. And we refer to these, this is a case, you could be both, you could do both. You could have an open neighborhood in the Euclidean topology, some interval around your point that lives inside of every neighborhood. For every, so we can partition these points in EX according to what happens here. Left accumulation points, right accumulation points. And I'll write down the basis of the topology. So this is a lot of, that's what we've just done. The topology looks something like this. The basis of neighborhoods at little x together with points to the left of the left accumulation points, sorry, intervals to the left of the left accumulation points, intervals to the right of the right accumulation points. What does that do for you? Just repeating that again. Well, more minimality comes into the story, monotonicity now. I'm not going to write down what the function is that we apply it to, but we can use it to get that there's a subinterval of our space on which this happens. In the closure of that interval, there are no accumulation points except maybe x itself. And now there are four possible things that can happen based on the left and rightness. Either x is a right and a left accumulation point of itself, in which case, looking just at this interval, a basic open neighborhood is an interval around x, or it's a left but not right, in which case basic open neighborhoods look like this, right but not left, in which case they look like this. Neither, in which case they're isolated. These are definable conditions. You have an interval J and four definable conditions. So partition your interval into four pieces according to which one holds where. One of those has to contain an interval, and on that interval you will have the corresponding topology. Okay. If you assume Hausdorffness, you can soup this up a bit. The key difference, the key extra ingredient you're using is uniform finiteness, because you can first partition according to how big these E accumulation sets are. There has to be a uniform bound on how big they are. So partition according to how big they are. And by monotonicity, if you define functions that pick out each of the points in that set in turn, you can actually say, again, the Hausdorffness comes in to say that they're not constant, but then by monotonicity, you can say that they've got to be strictly monotonic on each interval in this partition. And from there, you get a condition similar to the one we wrung out of things the last time around, which is you've got intervals whose points don't have any E accumulation points in that interval, except for the point it's maybe the point itself. And you can do something similar. So my point is there's one bit of model theory, which is the saturation argument. And then there's uniform finiteness, cell decomposition, monotonicity, all of the classic O-minimal tools and nothing else. Okay. All right. So that's decomposition theorems. That's what I wanted to say about that. I have a little bit of time left, if I understand correctly. So am I right?
Yeah.
So we are, right? So I'll just wave my hand somehow in the direction of some other types of theorems that you could try to prove. So that was T1 and then T2. So hey, what about T3 spaces? So what if they're also regular? And for this, I want to take a slightly different tack and talk about embedding results. And again, the motivation for that, or the original result for that somehow was about linear orders. So the result about definable linear orders, which is the sort of the peak of that series of work, is due to Ramakrishnan. And it says this, that if you've got a definable linear order, so a set P, which is definable together with an order relation on it, which is a definable set, dimension, and then there exists a definable embedding into a lexicographic ordering. Okay. And nicer things happen if you have extra structure, but don't worry about that. Follows that every definable order topological space is up to definable homomorphism induced by a lexicographic order. And this is what was used by all these people to classify definable economic preference relations and characterize which such relations emit a definable utility function, which is of interest in the economic preference theory. This is a big question when you have a continuous utility function for your economic preference relation. So definable is piecewise continuous. So this is a very nice result, not least because I think various economists are quoted as saying any preference relation you would ever encounter is going to be definable in a nominal structure. So this is somehow satisfies them somehow, let's say, which is good. Okay, but this, I wanted to mention the result there in the middle due to Ramakrishnan, because what can we say more generally if we have a definable topological space? Again, let me look at ones that are just one-dimensional. So here's the result in question. Again, I've written this in the line because it's much, much easier to state, but there is an analog for one-dimensional spaces in general. If you're in the line, your T3, so Hausdorff regular, definable topological space, up to a finite set, you can partition your space into two pieces. So the Y and Z here, one of which embeds definably into something that looks like this, lexicographic end split interval line, and one of which embeds definably into this kind, it's Alexandrov end line. Okay, so again, what do you use to prove this? Partition into finitely many points in open sets, such that each of the subspaces you've created can be embedded into a space of one of these forms and then glue everything together. And I kind of alluded to this earlier, it's possible to generalize this construction to one that makes sense for one-dimensional space. Okay, so that's one type of embedding result. What about the other type, which is the one that actually has some sort of history to it, which is affineness? So I've said all of this already, but I thought I should write it again because it's been a long way since the beginning of the talk. A definable topological space is affine if it's definably homeomorphic to Euclidean space. We've said that already. So some subset of the Euclidean space in R to the n. Yeah. The definable manifold space is affine if and only if regular. That's Van den Dries. Definable metric space is affine if and only if definably separable, whatever that means. Okay, what it means, I've put the definition on the slide. This is his definition of what it means for a definable metric space to be definably separable. If it does not contain an infinite discrete subspace. In metric space, that seems perfectly reasonable. The problem is it's not a hereditary definition. Separability is. So, or I didn't really want to get into this. I put the slide in anyway. This is a hereditary definition. Separability is not, is what I meant to say. For example, that one with two lines over there on the far side of the board. This is the earlier example I'm referring to. It does contain an infinite discrete subspace. Or not. This is not the right definition in general. So one of the things we had to do is come up with another direct definition, which is this: definably separable if there does not exist an infinite definable family of non-empty pairwise disjoint tau open subsets. If we can pass all of that, it might sound familiar and sound a little bit like the countable chain condition, which is equivalent to separability over the reals. So the good news is that so is this definition. So they're all equivalent over the reals, and it's the right thing to work with in general. So what you have to do to prove an affineness result for definable topological spaces in general, or let's say for one dimension, is really to look at when you are definably separable and definably metroid, leveraging Walsberg's result. So that's what we did, and the result, again, it sees, yeah?
So when you say
does not contain if a discrete set, you mean, when you say a subspace, you mean a definable?
Yes, it should say definable. Thank you. That's a good catch. Yes.
Okay.
Yes, sorry, that's a typo. Thank you. Yep, absolutely right. So again, I'm not giving you the proofs at this point in the game, but here's the statement that we have. Again, Hausdorff, one-dimensional. Exactly one of the following holds. Either you can obtain a bad subspace, so a subspace homeomorphic to maybe the right half open interval topology or the discrete topology, or you are in fact affine. So the whole thing is homeomorphic to a Euclidean space. So how do we, what are the ingredients that go into this? Well, we already know that you could partition your space into subspaces that are of one of those types at the top. So if you have right half open interval, left half open interval, or discrete, that's the first case. If none of those shows up, then really what you have is what you might call piecewise or cell-wise Euclidean. You just have to show that that is actually affine. The whole thing is then definably homeomorphic to Euclidean space. That takes some work. Here is the ingredients, a result of Andreessen definable quotient spaces together with a definable compactification result. What is definable compactification? Gal kind of already asked the question. What does definably compact mean? I could probably give an entire talk just on that. There are various characterizations. My student Pablo, former student Pablo, has a paper on that really sort of gives the definitive answer to many equivalences on that. I included the statement of the compactification result, but I won't spend any time talking about it because we don't have time, but there is a definition of one thing you could mean by definably compact. Those are completable, but there are many other definitions that you could use. Pretty much any classical definition of compactness you could think of, there's some kind of definable analog, and he's proved it there. So you do look for that if you're interested. All right, so I have about 5 minutes. I should mention, okay, for the interest of completeness, this has been going on for some time, as you could guess from the dates that have been showing up on the slides. Independently of us, around the same time we just proved the results I just mentioned, Peterzil and Rosel proved a very similar type of statement, and I wanted to mention that for the sake of completeness. This is our result again. You've seen this already briefly. Here is Peterzil and Rosel's result. It's an if and only if statement. So sorry, it's an equivalent statement. That you're affine if and only if you're regular and have finitely many definably connected components. We can show that this you can recover from this if you're assuming that you're working over a field. The nice thing about their approach, there are a lot of similarities about some of the definitions used, but their approach is much more theoretic in places. And that means that they can actually get a stronger result if you weaken some of the conditions on the structure and assume that X is bounded. It's very nice. All right, so what more can I just throw in for the sake of, remember this was supposed to be sort of an appetizer before dinner. So here's some more set theory. I don't know, that's not a sentence you'll probably ever hear again. Okay, so remember the motivation I threw out was for this what do you call it? Decomposition result that I gave you was this 3-element basis conjecture from Gruenhagen, which in turn I said was motivated by questions about perfectly normal compactness. So what is that? Perfectly normal compact Hausdorff spaces, where perfectly normal means normal and open sets are countable in those sets. Okay, the kinds of questions that people were interested in asking, I'm not going to explain the connections, to be honest. It's also quite difficult for me to understand what they are. This is a motivating question. Is something like the split interval over R, in essence, the only non-metrizable space that has all these properties? Okay, that's a question. Here are some conjectures that are related to that question. Due to Fremlin, according to Gruenhagen and Gruenhagen himself, every such space admits a continuous at most 2-to-1 map onto a compact metric space, or every such space contains a homeomorphic copy of some uncountable piece.
Parentheses ZFC means it is consistent with ZFC.
Yes, exactly. I'm surprised. Thank you. I'm glad that that's worth asking. Okay, all I will say is that we proved definable versions of these statements because it's that time of day. All right, but I'm happy to talk about the details if you're interested. And it basically combines all of the theorems that I've talked about today. So with the last 2 minutes, all I wanted to do was to say something about higher dimensions, because really all the theorems, except for the Brunebarbe sort of 3-element basis type statement, everything else was for one-dimensional definable topological spaces. So clearly you think there's room here, there's road ahead of us. So here was our affineness result for one-dimensional space, Hausdorff spaces. It's just repeating what we've already seen. It doesn't extend to higher dimensions. So that two-dimensional example over there, where you cut out these pieces of y equals x squared, that example over there, it's not affine, but it doesn't contain any subspace that's definably homeomorphic to one of these bad interval spaces up here. And in fact, all of its one-dimensional spaces are affine. We also have a two-dimensional example that I did not put on the board, which is sort of related to the bow tie topology, if that means anything, which is Hausdorff regular. It's not affine, but it is cell-wise Euclidean. So you can decompose it into cells on each subspace, each of which you have the subspace topology being the Euclidean topology. All right, so this needs a rethink, perhaps. So with my last slide, I will try to say what you might try to do instead. One of the things we proved along the way is that a one-dimensional definably compact space is affine if and only if it has frontier dimension inequality. So that's maybe something you could leverage. Certainly, in his thesis at least, Pablo tried to do that and showed something in higher dimensions, which I've written there, but don't worry about the details. There's something you might try to define called definably completely regular. If you have the FDI and you have this property in your Hausdorff, then you can show that you're affine. Maybe that's a thing you could try to prove holds more generally. Doesn't necessarily seem like the best approach at this stage in the game, though. Let me tell you what seems like a better approach. So after some effort, because this really is a delicate business trying to give the right definitions, Pablo has introduced what seems to be the right notion of definably second countable. I've not put it on the slides because it's definitely too technical for this point in the game. But the second is the dimension 2 example, the one I didn't draw on the board with the sort of vaguely bow tie type topology. It also doesn't satisfy, but one could conjecture that somehow that's the only obstacle, and that one has a sort of definable Eurozone metrization theorem. So what am I trying to say? That somehow Pablo's conjecture is that affine should be equivalent to being T2 regular, so T3, and definably second countable, according to this definition that I have given you. And it in fact holds for definable metric spaces. That's something that he's shown, and using our affineness theorem, you can say that it holds for one-dimensional definable topological spaces, because these two bad spaces do not satisfy this definition of second countability. So maybe that's the right statement to try and prove in general. It doesn't seem that easy to see how to do that, though. So this is definitely quite open. So that's maybe one direction this could all go in. But as I said at the beginning, what I would be interested in knowing are more examples where this classification or these embedding theorems could actually tell you something genuinely new about your space. So if this inspires anybody to think of an example that where we could maybe say something, I would be very interested to know about that. All right, I think with that, I'll stop here. Thank you very much.
Great, thanks, and excellent. Oh, so any questions?
You mentioned the elementary extensions once.
Yes.
Logical space. So now I understand you're sort of saying you have a definable basis, but a topology could be weird. Under elementary extensions, is there any consistency that happens with these topologies?
As in, if you, well, I mean, it's a definable basis, so it will define.
No, for sure. But if you take R and you extend it to some higher thing, then you want to understand the topology generated over there versus over here. Do they have similar properties? Because the topology itself is not definable, right? So the basis is definable.
The basis is definable.
My question is not making much sense?
No, I mean, I think it makes perfect sense. I would expect this to be preserved somehow. Maybe I'm missing something.
I guess maybe the question is, do you have a definable definition
Yes,
for
this
this
partition.
properties? Maybe sometimes your definition is not the same as the classical definition, right? So
Right.
that definition is preserved under elementary extension. But
So
maybe
in some
it's not
cases, it's a
equivalent.
definable condition, and in some cases, maybe not so clear, yeah.
So, but is it true? I mean, say compact, your definition is equivalent to compact. So do you have a definable definition such that, I mean, really now when you interpret over any O-minimal structure, what you define is compact in the point set sense, even only.
Yeah, I see the point. So I'm trying to, so there's a fair list now, but none of the ones that I can remember off the top of my head suggest to me that, so certainly the curve completion, every curve, every definable curve, I mean, you can't say that definably, so there's that doesn't work.
Yeah, compactness specifically is kind of usually, I don't know, tricky with this elementary, with ultra products. That's why I asked about that one.
Yeah.
Don't you just lose compact? Like if you take something that's definably compact, like unit interval in R, and then you just base change to like any saturated large extension that's not Archimedean, doesn't genuine on the notice compactness just disappear immediately?
Yeah, that's why I think when she's using, but she has a different definition of compactness.
But nevertheless, I would be concerned. So, yeah. Thank
You use metric at places. Can
Sorry,
it be
used,
at places you try to construct metrics?
yes,
Can it be easier to construct uniform structures? The system of things containing the diagonal with the same properties.
I'm not sure. So. Not quite sure I necessarily understand exactly what you're trying to, what we'd like to construct.
Uniform structure is what
Yeah.
André Weil was
Yes.
wanting to use instead of the metric to define the uniform convergence.
So I think there is some work on this, but whether it's easier or not, I wouldn't like to say. It's a bit slightly orthogonal to what we've
You
done.
don't really need, I guess, little triangles. Think somewhat weaker can be.
Yeah, so there's some work, I think, again by Walsberg and Simonyi on different topologies. There's something going on there, yes, I've just not. How it. Most of these examples, how it exactly relates is not clear, I think, at this point, but yes, it's definitely a good question.
Oh, I'm sorry.
You're fine. Well, someone, I don't know. Was there? Yeah.
That's a yes.
Can you do anything in the direction of like separability? Like if I ask for T0 but not T1, can you put some constraint on that? In terms of, definable topological spaces that are not T1.
So, sorry, what would you like to sort of be able to say in that situation?
I guess
There are, of course, examples, definable examples.
just that there aren't that many somehow. I mean, I don't know.
Oh, okay, yeah, okay. Certainly you can look up examples. The idea of being able to, that's a good question. It is, the ones at the bottom end somehow are always sort of artificial examples just to prove that you need to have certain conditions, but the idea of trying to see how many you could come up with is not something thought about. That's a very nice question.
So when can one define a Gofen by a definable equivalence relation?
When can one define what? Sorry, why
A Gofen by a definable equivalence relation.
Oh, that's
When is the quotient space also definable?
Yeah. So this is the result of Andries that I think I was mentioning. So. So you certainly need
The group, really.
You need, I was thinking you need the field. No, the group language is sufficient to, are we talking about just define like elimination of imaginaries? Yes, you just need yes, if that's the question, then you just need to have some presence of the group underlying your structure. So your expansion of a group would be sufficient. Actually, it's like definable choice is slightly less, but yeah, if it was about the result that we use, you need, for that we need. But if I've already answered the question, I should back away slightly. Please.
Maybe one,
Yeah.
So if you have a nice definable space like affine,
Sure.
is the construction which takes a point to the link around that point something that's invariant under definable homeomorphism?
That's a very good question. I do not know the answer to that. It's something to think about. Yeah. Unless anybody, no, that's something we know, clearly, something to be looked at. Very good. Thank you. Thank you. Very nice questions. Much appreciated. Oh, okay.
It's a quick one.
Okay, your theorem just reminded me of the graph minus theorem. It says that if you have a set of graphs which is close into taking minors, then the can be characterized by there being finite set of minors which have to be excluded. Your theorem is something of the form that you have some topological space defined by these properties, and it fits into one of these few buckets. Is this sort of a general structure of a theorem? Or you can say if you have a class of structures in O-minimality setup which is defined by being close into taking restrictions to subsets or something like this, then it has to be characterized by a finite amount of data. If that makes any sense.
I mean, from that limited information, it sounds as though it has a sort of minimal flavor, but I don't think anything in that direction is known for this concept. So again, a great question. Thank you.
Well, luckily Margaret's here all year.
Yes, I don't forget stipulations and so on.
But anyway, let's thank her. Yeah.